Okay, so now we get to the underdamped case. So in the underdamped case, it's important to remember that b squared minus 4mk is negative. So what we're given right here is going to be negative under the square root, so this will be imaginary. And so it's going to be necessary to pull out Euler's relationship, which is given, and all of the relationships that we had at the top of the page, including Euler, in order to make this work. Okay. Now we're supposed to show the solution is what I have at the bottom here. And remember, this isn't part of what you have to do, but this is decay, exponential decay. And this was the, right here, this would be the undamped solution, with the exception that omega no longer equals omega naught. Okay, so we have a new oscillation rate because of the damping. It will slow things down a little bit. And we have exponential decay as well. So our oscillations will die down. All right, so we just have a decaying oscillation of what we had before. But let's show that this works. Okay, so start with the given. We can start with r equals negative b plus or minus the square root of b squared minus 4mk all over 2m. All right, now we can do the same steps that we did before. Okay, so let me just go through those quickly. R equals, and we can write negative b over 2m plus or minus the square root of b squared minus 4mk all over 4m squared. So far this is just a replication of what we had in 2b. This becomes negative gamma plus or minus the square root of, and then we can do, let's go right to b over 2m squared minus k over m. Okay. Actually, I should probably be symmetric here. So it would be better to leave this. We want to keep symmetry in our problems. So keep b and m until we replace all of them. Okay. So now in this step, we can say this is negative gamma plus or minus the square root of, this is gamma squared minus omega naught squared. Okay. But it's important to note that if what we had up here is negative, the rearrangement will still be negative. What I'm writing in red does not need to be written in your proof for this. We can assume that that would be true. All right. So what we really want to do is we want to have a positive expression under the radical. Okay, so what I can do is I can turn this into the negative of omega naught squared minus gamma squared. Okay, now you'll realize, okay, that's what we have in the red box. It's the last relationship, omega naught squared, the angular frequency without damping minus the damping constant squared should be, oh, there's a mistake in that formula, should be omega squared. We need symmetry there. Okay, so that will be omega squared, what we have in here. All right, well, we can rewrite that as negative gamma plus or minus. We have the square root of negative 1, and we have omega squared. So this becomes the square root of negative 1 times omega squared, which you hopefully realize is I. So R equals negative gamma plus or minus I. Whoops, and we made a mistake in the last step. When we brought omega squared out of the square root, it just became omega. So this simply becomes I omega. In fact, if you jumped from over that step, that would be perfectly fine. When we have the square root of a negative number, it will be I times that number. Okay, so you can jump right over that middle step. So this isn't really necessary to write in. I would assume that you can take the square root of negative omega squared, realize it will just be omega, and that it will have to be multiplied by I. Okay, so this is R. That means R1 is negative gamma plus I omega, and R2 is negative gamma minus I omega. Now we need to put that back onto the general solution. Remember, the solution for all of these was that x is equal to C1 e to the R1t plus C2 e to the R2t. Okay, so what happens here, x is equal to C1 e to the negative gamma plus I omega t plus C2 e to the negative gamma minus I omega t. Whoops, I omega parentheses, the quantity, times t. Okay, so that's our solution. We need to somehow, though, make it look like it's an exponential decay times the sinusoidal part. Okay, so what we have to do is we have to extract, well, we first need to rewrite these terms as factors. Okay, so we get e to the negative gamma t times e to the I omega t. You don't need to show this, but let me just put this on the side. If you have e to the a plus b, that is equal to e to the a times e to the b. Usually we go the other way. If we have a base raised to two different exponents, we add the exponents. In this case, the exponents were being added and we broke it up into two factors. Okay, so we can do the same thing with the second one. And we can make this into two factors, e to the negative gamma t and e to the negative I omega t. Okay, so if you were to add those exponents, you would get back to what you had in the line before. All right, now that's good because we have the e to the negative gamma t, which can be drawn out. We need that to happen. That was part of the solution we're striving to attain. And then what's left inside is C1 e to the I omega t plus C2 e to the negative I omega t, right? Now, in order to make this work, I probably should have said the following. Okay, I probably should have, instead of putting those in as C1, I should have made those A's when we get down to this step. In fact, let me just do that. The constants hadn't been defined yet. So I'm just going to call those A1 and A2 at this point, because if you look at what we have for Euler's equation, we could then rewrite that as x equals e to the negative gamma t times C1 cosine omega t plus C2 sine omega t. And we've reached the grand finale. All right. So you could put the A1, A2 in at this step, or you could have put it in at any step above that, and it would still work out. And even if you had C1 and C2, I would be okay with you just carrying that all the way through. Do know, though, that these constants are complex numbers. The A1 and A2 need to be complex in order for things to work out, whereas C1 and C2 are going to be real numbers. Okay, that is the most complicated of the derivations. I hope you have fun with it.